Good morning. Today I have some case studies on zirconia and zircon. And I mentioned that each composition of refractories is a little different in how you design them for thermal shock resistance. So we'll do zirconia and zircon today, silicon carbide and silicon nitride on Thursday. And then next week we'll spend the whole week on the composites, the carbon matrix materials, which were designed just for basically thermal shock resistance and also corrosion resistance. So they're far superior to all these other refractories we've been talking about. So this first case study, they looked at the effect of the stabilizing additions on the thermal shock resistance of zirconia. So they correlated the thermal shock behavior of zirconia with the monoclinic phase content. And they used CaO and MgO as the stabilizing agents. And basically the quantity of the stabilizing agent, the amount of the stabilizing agent that is used, has to be less than that's required to stabilize zirconia totally in the cubic phase. So CaO and MgO contents have to be less than required for complete stabilization, because you want to keep some of the monoclinic phase present. That increases the thermal shock resistance. When it goes through the transformation, it makes micro cracks and so on. So this paper and then the following paper are in a Russian journal, and they're translated, and I think the translation is pretty good. So this was earlier work from 1967, and then there's a follow-up on that a year later. So they used a high purity zirconia, about 97% purity. The lime, CaO, was from a calcium carbonate, a pure calcium carbonate. The MgO was from a pure magnesia. And then the CaO was varied from about 6.5 to 20 mol% addition to ZrO2, and the MgO was 12 to 20 mol%. And then they also used a combination of lime and magnesia, 14 to 18 mol%. So at the lower end, like 6.5 is not enough to stabilize zirconia totally in the cubic phase, but 20 mol% should be. So they form briquettes or pellets. So they press pellets or briquettes, and they fired them at 1750 degrees C. And then they used X-ray diffraction to look at how much monoclinic and cubic phases were present. So the zirconia stabilized with 6.5 to 13 mol% lime, contained both the monoclinic and the cubic phases. And then the zirconia stabilized with the higher lime content, 17 to 20 mol%, was all cubic. The zirconia stabilized with anywhere from 12 to 20 mol% MgO, contain both monoclinic and cubic phases. And then the zirconia stabilized with 14%, and that's a combination of lime and magnesia, contain both monoclinic and cubic phases. But when they went to a higher content of this combination, lime and MgO, 18%, it was just cubic. So then they took these briquettes, they crushed them, pressed them into shapes that would give rise to the right kind of samples. And then they were refired at 1750 degrees C. So after this second firing, we now have samples suitable for testing. The zirconia stabilized with the 6.5 mol% lime, contained the monoclinic and cubic phases, but now the other zirconia compositions stabilized with the higher lime content, 13 to 20 mol%, was all cubic. And then the zirconia stabilized again with MgO, 12 to 20 mol%, still contained monoclinic and cubic. And then all of the zirconia stabilized with the lime and magnesia combination from 14 to 18% was just cubic. So the type of thermal shock cycle they used, they started at room temperature, heated it to rapid heating to 1600 degrees C, and then rapid cooling to 20 degrees C in an air environment. So this was a heating and cooling cycle, heating at 1600, cooling to room temperature. And the number of heating and cooling cycles was a function of the weight loss. So they kept heating and cooling until they reached a 20% weight loss. I don't think the sample size was specified in this translation, but typically they're following an AST, a German DIN test, which is a 50 millimeter diameter cylinder by 50 millimeters high. So it's a cylinder, and it's cycled until you reach a 20 weight% loss. And usually if there's no weight loss, they just stop it at around 30 cycles. So these are the batch numbers, 11 through 18. So 11 through 14 had a lime stabilizer, and these were the 3 mol%, 4 mol%, 6.5, 13, 17, and 20. And then in the briquette they pressed, this was the X-ray diffraction analysis. So 6.5 had 85% monoclinic, 15% cubic, 13% had 5% monoclinic, and 95% cubic. And then the 17 and 20 mol% lime additions was all cubic. And then they refired it after they crushed the briquettes, pressed them into samples. So 6.5 mol% lime was 60% cubic and 40% monoclinic. And then the other 3 at 13, 17, and 20 were all 100% cubic. And then the thermal shock cycles, 20 degrees to 1600, back down to 20 degrees. These are air heating cooling cycles. So the material with 40% monoclinic on average lasts between 14 and 16 cycles, whereas the 3 materials that were all cubic only lasted 1 or 2 cycles. So the MgO material was done at 12 and 20 mol% MgO, and the briquettes at 12% still had 45% monoclinic, and at 20% at 25% monoclinic. And then in specimen form, 15% monoclinic, and then 5% monoclinic. So the material with 15% monoclinic zirconia lasted 5 to 10 cycles, and then the material with just 5% monoclinic only lasted 2 cycles. And then the 2 materials with the lime magnesia combinations, this was 6.9 and 7.2. This was 11.3 and 6.5. After firing to 1750 to form a specimen, they were all cubic, and they only lasted 2 cycles here and 1 cycle here. So the materials with a 40 and 15% monoclinic phase did pretty well compared to the all cubic phase materials. So briquettes were crushed again, same initial briquettes, they were pressed into specimens, but this time they added 10 or 20 mole% additional monoclinic zirconia, and they were refired at 1750 degrees C. So they're increasing the monoclinic zirconia content with direct additions. So the zirconia stabilized with the 6.5 or 17 mole% lime contained both monoclinic and cubic phases. And then the zirconia stabilized with just 20 mole% lime contained just a cubic phase. And then the zirconia stabilized with anywhere from 12 to 20 mole%. MgO contained both monoclinic and cubic. And the same for the zirconia stabilized with the lime magnesia combination, anywhere from 14 to 18 mole%. Again, contain both monoclinic and cubic. So they're just trying to increase the monoclinic content because in the firing process here, they pretty much went to cubic or low monoclinic contents in this first experiment. So now the batch numbers 11 through 18 are modified. So there's an M after them for the additions. So an M, there's a 10% zirconia, monoclinic zirconia addition, and a 2M just means 20 mole%. So there's also something else to consider. The stabilizing oxides tend to diffuse or migrate, and that also decreases some of the zirconia in the monoclinic form. So 11 through 14, again, were lime stabilized, 15 through 16 were MgO stabilized, and then 17 and 18 were a combination of lime and magnesia. This, again, is the content of the additives in the briquette form, same as before, and now there's a 10 or 20% addition of monoclinic zirconia. And then for the X-ray diffraction, this is the cubic phase, this is the monoclinic phase. You can see there's quite a bit more monoclinic phase present. This one is 45 to 40. This one is 55 to 60. And then the 13 mole% in the briquette still had 15. And then the two higher lime contents were less than 2, and this one was all cubic. The MgO materials at 25, 40, and the highest level of the MgO stabilizer only had 2 to 3% monoclinic. And then the lime magnesia combination was 6.9 and 7.2%. Still had 35 to 40% monoclinic, but the material with both lime and magnesia with the higher stabilizing content only had 2 to 3. So there's quite a bit more monoclinic zirconia in this group of modified materials. So here's the calcium, magnesium, and the calcium and magnesium combination. This is the original mole%, and then this is with additions of 10% monoclinic and then 20% monoclinic. So this is the thermal shock resistance cycles again, heating and cooling 20 degrees to 1600, back down to 20 degrees C. So this one with the highest monoclinic content survived 30 cycles. And I'm pretty sure they're following the DIN version, the German thermal shock test, where they stop it at 30. So these samples did rather well, and I'm sure that it was just stopped at 30 cycles. And then you can see 13% had quite a bit of monoclinic, 9 and 14 cycles. Then these last two had 15 and 2. So they're much lower. And then the magnesia stabilized material with the highest monoclinic at 12 and 16, and then with the lower contents, we're down to 5 and 2. And both of these had lower monoclinic contents and 3 and 8 and 5 and 8 cycles. So the number of cycles to a 20 weight percent loss is pretty much a function of the monoclinic content. So if they plotted thermal shock resistance, heat cycles from 0, and this goes up to 30, and weight percent or mole percent, lime. So number 1 was without any monoclinic zirconia present, and 2 was with 10% monoclinic zirconia, and then this graph number 3, 20% monoclinic. So you pick any amount of stabilizer for weight percent or mole percent CaO, and you go up here, and you can see that, as you say, let's look at 6, there was probably 2 cycles here without monoclinic zirconia, maybe 10 cycles here with 10%, and higher than 15 cycles with 20%. So this just shows the higher the monoclinic zirconia content, the higher the number of thermal shock cycles it can withstand. So I mentioned that what they call migration of stabilizing oxides, that's really MgO and lime diffusing in the material and reacting and converting some of the monoclinic zirconia to cubic. So even during this heating and cooling cycle, I think it was held about a half hour at 1600 to stabilize it. This diffusion or migration of the oxides, the stabilizing oxides, was changing the zirconia content. So for batches 11 M and 11-2M, this was the initial lime content in the briquettes. This was the additional 10 or 20% added of monoclinic zirconia. And this is before thermal shock, and then this is after thermal shock. So this was 40, 45% monoclinic, and it decreased to about 30. This was 60 to 55 monoclinic, and it decreased to about 25%. So it is actually changing during the thermal shock cycles. So what they concluded on the microstructure, the improved thermal shock resistance for samples with greater than 15, this is mole percent, monoclinic zirconia. So anytime they had greater than 15 mole percent monoclinic zirconia, they had improved thermal shock resistance. And that's because these circular cracks formed around the coarser monoclinic grains when they went through the polymorphic phase change. So the monoclinic to tetragonal phase change, tetragonal is denser, so there's a volume decrease when it goes to tetragonal, and when it goes back to monoclinic, there's a volume increase. So that creates cracks around the coarser monoclinic grains, and that increase in crack density, as we've talked about, gave rise to improved thermal shock resistance. So zirconia is a little different. They're using the phase change in this material to create higher crack density to improve the thermal shock resistance. So the second example here is a year later, the same group of investigators, and they looked at the phase composition on the thermal shock resistance of zirconia. So they looked at this in a little more detail. So the poor thermal shock resistance of zirconia refractories is due to this monoclinic to tetragonal phase transformation between 930 and 1230 degrees C. So that's the temperature range where the phase transformation takes place. This is an unstabilized zirconia refractory. So as we noted when we talked about thermal expansion, this phase transformation will really disrupt the structure. But if you stabilize it in a cubic form, you eliminate this phase transformation. So the previous paper I just mentioned, they're looking at small amounts of monoclinic, actually using the monoclinic phase in small amounts to improve the thermal shock resistance. If it's 100% monoclinic zirconia, it probably won't even survive the thermal shock because of this phase transformation. So if you look at the thermal expansion of the different phases, monoclinic is 7 times 10 to the minus 6 per degree C. Tetragonal is much higher, 12 times 10 to the minus 6 per degree C. And then the cubic is in between 10.5 times 10 to the minus 6. And it actually, depending on the structure, could be as high as 15 times 10 to the minus 6. So the thermal expansion coefficients are variable. Tetragonal and cubic are quite high, monoclinic slow. And the thermal conductivity is not very high. It's 2 watts per meter degree C. So it's on the low end for refractories. So you can improve the thermal shock resistance by incompletely stabilizing zirconia or adding monoclinic zirconia. So when you add this monoclinic phase, it decreases the modulus because of the microcracks that are created. And adding more monoclinic with the low thermal expansion coefficient decreases the coefficient of thermal expansion. So by partially stabilizing zirconia, you're lowering the thermal expansion coefficient and you're creating microcracks that decreases Young's modulus. It's also going to decrease the strength. So they started out with a zirconia of about 97, 98% purity, and they stabilized it with the calcium carbonate, a chemically pure calcium carbonate. Similar to what they did last time, they formed pellets or briquettes by pressing these powders. They sintered at 1750 degrees C, and then they ground and sized these materials, keeping the maximum grain size about 2 millimeters. Those powders were repressed and fired again at 1750. They wanted to look at the effect of sample shape, so they pressed rings, cylinders, and cubes. So a ring was 30 millimeters in diameter. That was their outside diameter. The inside diameter was about 22 millimeters, and it was about 25 millimeters tall. Cylinders were about 25 millimeters in diameter and 35 millimeters high, and the cubes were 50 millimeter on all 3 edges. So they looked at 3 different shapes. They measured Young's modulus at room temperature. They measured the thermal expansion coefficient from room temperature to 1,000 degrees C. And they measured both tensile and compressive strength at room temperature. The tensile strength was measured in what's known as diametrical compression. So it's not exactly a true tensile test, but it's very close. So it's not a pure tensile test, but it's pretty close. And they looked at 3 different heating cooling cycles. from 30 to 1300 to 30 degrees C in both air and water quenching, 30 to 1600 to 30 degrees C in air and water quenching, and then 30 to 2200 degrees C back down to 30 degrees C in air and water. So they went to a very severe thermal shock sequence here. Zirconia is a high temperature material. It's useful to this temperature, but this is very severe thermal shock, especially in water from 2200 degrees C. And they did the same thing here. The number of heating and cooling cycles were repeated until you get a 20 weight% loss. So there were 5 compositions. Zirconia content was around 92, 93%. And then the stabilizer, the lime, was around 5 or 6%. And then you have your other impurities adding up to 100%. Silica, alumina, titania, iron oxide, MgO, and the alkalis, sodium and potassium. There's also hafnium, trace amounts of hafnium present in the zirconia. So after firing, this is the monoclinic phase content. This is the cubic phase content. So one was 100% cubic, and then 2, 3, 4, and 5, 8 to 10, 15 to 20, 20 to 26, and 30 to 40. So increasing monoclinic content. The porosities were fairly similar. There's some variability in the density. They're all maybe 4.3, and this one's a little higher, 4.5. They also measured the permeability to see if this porosity was interconnected. So at the higher monoclinic phase content, there was some permeability. I suspect as the monoclinic phase content went up, the microcrack density went up, so that there's a little bit more permeable on these higher monoclinic materials. So the compressive strength and the tensile strength, kilograms per square centimeter. So they both decreased with increasing monoclinic phase content, and that's simply because of the increased cracks, increased flaws, decreased both compressive and tensile strength. So these are, they looked at compositions over here 1 through 4 for the thermal shock test. And this table is for heat cycles 30 to 1600 to 30 degrees C. And this is the monoclinic phase content from 0 to this range, 20 to 26%. And this is the same tensile strengths we just showed, decreasing with increasing monoclinic phase content, and the thermal expansion coefficient. So it also decreases with the monoclinic phase content because the lower thermal expansion coefficient of the monoclinic phase. Along with the decrease in strength, you have a decrease in elastic modulus. This is times 10 to the minus 4 kilograms per square centimeter. So that decreases with increasing monoclinic content. And then this is the tensile strength divided by the elastic modulus and the thermal expansion coefficient. And that's basically our R parameter. It doesn't have Poisson's ratio, but it is basically the R parameter. So it is increasing with monoclinic zirconia content. But again, these are low numbers, and I don't know how well the R parameter applies, but these are low numbers. And because of the decreased elastic modulus here and the decreased thermal expansion coefficient, this number is going to go up. So supposedly, composition 4 is better than composition 1 in resisting crack initiation, but this is 90 degrees, and we're thermal shocking something at 1600 degrees C. So the thermal shock resistance at 20 weight percent, loss 2 to 5, 2 to 4. So the first two aren't very good, but the higher monoclinic contents, 15 to 25, and then 15 to 40 cycles for the highest. So there's a substantial improvement in thermal shock resistance with increasing monoclinic content. So this is the effect of the shape of the sample: cylinders, cubes, and rings. This was the temperature range, 30 to 1300 to 30 degrees C. This is a higher temperature range, 30 to 1600, back down to 30. And these materials were in the 15 to 20% monoclinic range. And this was water cooling, and this was air cooling. So if we look at the means here, that's the average number of cycles before 20 weight percent loss. Water cooling is pretty severe, going from cylinder to cube to ring, 14, 12, and 10. And then the higher temperature from cylinder to cube to ring is 5, 5, and 1. And then air cooling is much less severe than water cooling. So going again from cylinder to cube to ring, it's 38, 35, and 14. And cylinder to cube to ring, the higher temperature, 12, 9, and 9. So the ones that did the best were the cylinders and at the lowest temperature. So the rest of the test conditions in this paper, they're just looking at cylinders, whether it's 1300 or 1600, 38 or 12 cycles. So they're just going to use cylinders and air because this gave the least amount of damage. So this is a cylinder, and we're looking at the end of the cylinder here. My guess it is about 50 millimeters in diameter, 50 millimeters tall. This is what it looks like one cycle at 2200 degrees C, the highest heating cooling cycle range. You can see there's a crack right down the center. So one cycle, it basically cracked right down the center. So the internal tensile stress has exceeded the tensile strength of the sample after one heating cycle. And these are diametral cracks following the diameter of the cylinder. So here is another example. Looking at the end of the cylinder, you see A here is a diametral crack from the thermal stress, and B is a diametral crack from a compressive stress. So this is put in a mechanical test machine, and it's loaded along the diameter. So it's compressed along this diameter. It creates a tensile strength, a tensile stress in the perpendicular direction. So the tensile stresses are perpendicular to this crack, and it's a diametral compressive test that produces this type of tensile failure, which is exactly what the thermal stress is doing. So this is how the tensile stress was measured in diametral compression. So if you plotted residual strength versus the number of heat cycles, this is the residual compressive strength after a number of cycles in air, but it's from 30 degrees C to 2200 degrees back down to 30 degrees C. So 0 to 9 heat cycles and residual strength from 0 to 100. So graph 1 is no monoclinic. Graph 2 is 8 to 10%. 3 is 15 to 20%. 4 is 20 to 26%. And 5 is 30 to 40% monoclinic. Again, these are the cylinders. So you can see one doesn't do very well. It's 2 cycles. So there's zero residual strength after 2 cycles. And then 2, 3, 4, and 5, as the number of increases, the percent monoclinic increases, these curves shift upward. So they're retaining more strength as a function of the heat cycle. So the higher the monoclinic loading, the better the thermal shock performance. This is pretty severe, 2200 degrees C quench in air. And then this is residual strength versus heat cycles. This is tensile strength. This was compressive strength. This is tensile strength measured by the diametrical compression. Same trend. They looked at compositions 1, 3, 4, and 5. Going from 1 to 5, you increase the monoclinic phase content. And as you increase the phase content, you increase the thermal shock resistance. So this is kind of a summary. Batches 2, 3, and 4, their densities. These are all different samples. So here, 4 samples were tested here. Looks like 7 here and 7 here. Their porosities. The number of heat cycles, well, the first sample was not tested. That's basically a control, but I think there were at least 5 in each one of these groups. So it's an average. The number of heat cycles, it went through. And then the compressive strengths, and then the change in strength, whether it was an increase or a reduction. So these were compressive strengths using the 1600 degrees C cycle, and 2, 3, and 4 are going up in monoclinic phase content. So these are the compressive strengths. And the thing to point out here, some of these strengths increased when they were heated at 1600 degrees C. So there was some crack healing taking place in these materials, especially at the lower monoclinic content materials, and then a few increases here. So there was some crack healing taking place. So what they did here to prove that, this is the residual compressive strength after these cycles in air. But instead of rapid heating or rapid cooling, they went up slow, a slow heating rate and a slow cooling rate. So they didn't thermal shock the material, but you see the residual strength went up here and eventually started going down. This is evidence of crack healing taking place. So they were able to isolate crack healing without thermal shocking the material. And they did a further experiment, and I could never tell where the interface was here, but I think it's right down the center. They took 2 pieces of zirconia, polished sections, placed them together on their polished surfaces, and held them for 30 minutes at 1700 degrees C, and the materials joined. So what that simulated crack where the 2 polished surfaces met completely joined or healed during this heating cycle. So in terms of the summary here of what they did, the microstructure, they improved the thermal shock resistance for samples that had 20 to 40% monoclinic zirconia. And in terms of the microstructure, there's a network of these annular or circular cracks that formed around the coarse monoclinic grains. And those cracks were simply a result of the monoclinic to tetragonal transformation. And they noted that the cyclic heat exchanges, as you cycle the temperature, there was a reduction in the monoclinic zirconia due to they called it a redistribution of calcium oxide. The calcium oxide is diffusing and stabilizing some of the monoclinic zirconia in the cubic form. So there's a reduction in the capacity to maintain the original micro crack structure, and that will also lead to a failure if you lose this micro crack structure due to crack healing. So this one is more recent, a 1990 study, the grain size dependence of thermal shock resistance. Now, this was a yttria stabilized zirconia. So the thermal shock of a yttria doped tetragonal zirconia polycrystalline material was evaluated as a function of grain size. So the critical quenching temperature difference, the fracture strength, the fracture toughness was measured as a function of grain size. And then they used a Raman microprobe to examine how much tetragonal or monoclinic phases they had present around these different cracks that were introduced by the thermal stresses. So they tried to monitor the phase content of tetragonal and monoclinic zirconia around the crack tips. So yttria dope zirconia has a high fracture strength, 800 to 2,500 megapascals. It also has high fracture toughness, 7 to 10 megapascals square root of meters. And the thermal shock resistance is smaller than you would expect based on a high fracture toughness and high strength. So a mechanical versus a thermal stress. The mechanical stresses have a high degree of transformation around the crack tip. And thermal stresses appear to have a lower degree of phase transformation around the crack tip. So the resistance to tetragonal to monoclinic phase transformation decreases with increasing grain size. So the larger the grain size in these polycrystalline materials, the greater the degree of transformation, and that should give rise to a greater thermal shock resistance. So this is a partially stabilized zirconia with a yttria stabilizer. So ZrO2 was mixed with about 2 mol% yttrium oxide. These are hot isostatically pressed. These are small pieces, 5 millimeters by 30 millimeters by 50 millimeters, hot pressed in the range from 1400 to 1700 degrees C. And then from these hot press plates, samples 5 millimeters by 2 millimeters by 15 millimeters were machined. SEM, scanning electron microscopy, was used to determine the grain size. And the mechanical properties were measured at room temperature, 3-point bend strength for the fracture strength, and the fracture toughness was measured by an indentation fracture method, usually using a Vickers hardness tester. And the thermal shock was the various temperatures were quenched into 0 degrees water. And then the Raman microprobe was used to examine the tetragonal and monoclinic phases around the thermally induced cracks. So these were the pre-sintering temperatures. Then they were hot isostatically pressed. So they were pre-sintered. There's still residual porosity here. Then they were hipped to densify them. The higher the pre-sintering and hipping temperatures, the bigger the grain size, from 0.4 all the way up to 3 microns. The bend strength basically decreased with bigger grain size, but the fracture toughness increased with larger grain size. So it was more difficult to propagate a crack in the coarser material. And these are the relative densities. They're all basically 100% dense. So they looked at the critical quenching temperature difference before a fracture took place as a function of grain size. And this is in degrees C, so this is about 250 degrees C, went up to maybe 425 degrees C from the finer to the coarser grain size, from about half micron to 3 microns. So the higher the grain size, the bigger the critical quenching difference. So they looked at this critical temperature, delta TC. This is basically the equation that we developed a few classes ago. This is R prime, taking into account the thermal conductivity, the sample size, and the heat transfer coefficient, and the shape factor. This was the simple R for a plate, if you recall, the fracture strength, 1 minus Poisson's ratio divided by the thermal expansion coefficient, Young's modulus. And this is the shape factor, which also accounts for the conductivity, K, Rm, half the sample thickness, and H, the heat transfer coefficient. So all samples were near theoretical density. So nu, the Poisson's ratio, A, the thermal expansion, E, Young's modulus, K, the conductivity, Rm was also held the same, and H, the heat transfer coefficient, should all be the same. So that there should be, if we keep all these variables the same except for the strength, there should be a relationship between delta TC and sigma F, but they didn't really see any clear relationship. But they said there was a relationship between the fracture toughness and the critical temperature difference. So the fracture toughness is increasing here, and that seemed to follow higher fracture toughness, higher delta T. The strength actually went down with increasing grain size. So the Raman microprobe, they looked around the crack tips. So this is intensity versus wave number. And so the peaks correspond to either tetragonal or monoclinic. So this peak is, for example, tetragonal. This one's tetragonal. These two are monoclinic. So the grain size goes from 0.4, 0.89 to 1.58 to 3 microns. So the intensity of the monoclinic peaks, these peaks labeled M, is increasing with grain size. So you can see the peaks are very small here, and as we go up, they increase in intensity. So there's more monoclinic phase present around the cracks in the coarser material. So this is the critical, again, the critical quenching temperature, and this is the intensity of those peaks. So increasing amounts of monoclinic phases formed by the thermal stresses, that gives you your higher delta T. So they found the intensity ratio of the monoclinic to tetragonal phases around the crack tips introduced by thermal stresses. That ratio increased with the greater grain size and gave rise to a higher delta T. Wrong way. So the thermal shock resistance and fracture toughness increase with increasing grain size. The increased grain size increased the contribution of transformation toughening from the thermal stresses. So the larger particles of tetragonal zirconia, it was easier for them to transform under the thermal stresses. And then the tetragonal to monoclinic transformation produces a volume increase near the crack tip. Monoclinic is a lower density than tetragonal. that increased volume near the crack tips puts a compressive stress on the cracks and stops the crack growth. So they really looked at the crack initiation issue here with the R parameter, and basically increasing grain size resulted in more transformation of tetragonal to monoclinic, and that compressive stress at the crack tip gave rise to better resistance to crack initiation. And then the last material here is actually a composite material. And we're looking at zircon, the silicate version of zirconia, the zirconia silicate. So they used silicon carbide inclusions to improve the thermal shock resistance of zircon. This is a 2009 paper. So the thermal shock of a zircon silicon carbide composite with 30 weight% silicon carbide was evaluated and compared to pure zircon. And these materials have the same porosity level, so they eliminated the effect of porosity. So the retained strength after thermal shock is significantly improved with the use of second phases. Second phases that have high strength, high thermal conductivity, low elastic modulus, and low coefficient of thermal expansion in general will improve the thermal shock resistance. So the raw materials were zircon, SiO4, 4-micron diameter particle size, and the silicon carbide was a larger particle size, 13 microns. So there was a pure zircon and a composite composition. The pure zircon was all 100% SiO4, and the composite was 70% zircon and 30% silicon carbide. These were pressed and sintered at 1600 degrees C in an inert atmosphere to prevent oxidation of the silicon carbide. So they were sintered under argon. They looked at the phases present by X-ray diffraction. They looked at the microstructure by scanning electron microscopy. They measured fracture strength and 4-point bending at room temperature. And these were the size of the bend bars, 52 by 13 by 3.5 millimeters. And the thermal shocks were variable temperatures from 100 to 1,000 degrees C. All the quenching was done in 25 degrees C water and on the same size bars. So this is for pure zircon. This is intensity versus angle here for these different X-ray diffraction peaks. The solid circle is zircon, and then the triangle is monoclinic zirconia. So you can see how intense the peaks are with the circles. So it is primarily zircon, but there are some smaller peaks for monoclinic zirconia. And what happens with zircon when you heat it higher than about 1450 degrees C? These were heated to 1600 degrees C. The zircon dissociates into ZrO2 and SiO2. And so some dissociation took place, and now we end up with monoclinic zirconia plus zircon. There has to be some probably amorphous silica present also. This is a cross-section of a sample of the zircon silicon carbide composite. You can see it has a black core and a white surface. And this is after heat treating. So this is a schematic of the cross-section of a sintered zircon SiC composite. There's a black core and a white coating. So the core was zircon, some SiO2, and SiC. So we started out with zircon and SiC. There must have been some oxidation or dissociation of the zircon. And then the coating was zircon, silicon carbide, a monoclinic zirconia, and SiO2. So the surface started to dissociate first. So we now have 4 phases instead of 2, and apparently some SiO2 in the center. So it's primarily zircon, silicon carbide with a trace amount of SiO2. This is primarily zircon and silicon carbide, but now we have small amounts of the zircon that's associated as monoclinic and zirconia and SiO2. So this is the zircon silicon carbide composite, and there's X-ray diffraction patterns of A, the core, the black center, and B, the coating, the white coating. And again, these are centered at 1600 degrees C. The circles are again zircon. The triangles are monoclinic zirconia. The squares are cristobalite. That's the SiO2 that crystallized the cristobalite. And then the triangles are silicon carbide. So B is the coating. You, you can see the triangles here. If you look down, there's quite a bit of monoclinic zirconia on the surface, none in the interior. And there's some cristobalite on the surface and a little bit in the interior. But the monoclinic zirconia is on that white area. So they looked at retained strength versus quench temperature difference. So this is basically your room temperature strength. And then this is quenching from 1000 degrees C back down to room temperature. So this is before thermal shocking, and these are after thermal shocking at 100, 200, 300, 600, 800, and 1000 degrees C. So the open bars are zircon, and the black bars are zircon with the silicon carbide. So you can see how much stronger the material was without the silicon carbide, but it also decreases substantially with quench temperature and really falls off at the highest temperature. But the composite material of the zircon and the silicon carbide pretty much stays the same. And then it starts to exceed the pure zircon at the higher temperatures. So this is basically how they're designing a thermal shock resistant material. They're making it weaker. Its retained strength is low, but it is staying constant. It's not having this large decrease in strength. So flexural strength loss versus temperature difference. The squares are the zircon, the circles are the composite. So you can see how much higher the strength loss in percentage was for pure zircon compared to the composite material. So even though the composite material started out with a lower strength, it doesn't lose as much strength as the pure zircon. The porosities were about the same. Z is zircon, ZS is the zircon composite with silicon carbide. The bulk density changes because SiC is lower density than zircon, but they kept the porosities the same to eliminate the effect of the pores. The pores would enhance the thermal shock resistance. So this is an SEM image of the composite material. This was centered at 1600 degrees C. There are silicon carbide grains in a zircon matrix, and then these open areas are the pores, the black areas. So the pores are about 2 to 3 microns in diameter. So silicon carbide and a zircon matrix. So they looked at R4 prime, which was in this case E, Young's elastic modulus, the fracture surface energy gamma, and that's divided by the strength squared. So the high initial strength of pure zircon, remember it was much higher than the composite, and it's squared. That gives a very low R4 prime for the zircon, uh, pure zircon material. So in terms of the results, the microstructure, zircon, the surface layer of the zircon silicon carbide composite started to decompose, and the zircon silicon carbide composite exhibited improved thermal shock resistance because of higher retained strength compared to pure zircon. In spite of its low initial strength, it still had higher retained strength than the pure zircon material. So that's what I have on some examples of zirconia and zircon. Carefully controlling the amount of the monoclinic phase controls the crack density and controls the thermal shock resistance. So next time I have some examples of silicon carbide and silicon nitride materials. They have some different issues with oxidation. This material had an issue with phase transformations. And then we'll spend quite a bit of time on the composites, carbon matrix composites. They're primarily a flake, graphite, and a resin with vastly improved thermal shock resistance. So again, thanks for listening in today, and I'll see you on Thursday. Have a good rest of your day. Thank you.